Hello, and welcome to this presentation on compositional verification of smart contracts through communication abstraction. I'll start this presentation with some background and some motivation. I'll look at what smart contracts are, why we care about verifying them, some challenges in smart contract verification, and current approaches to solving these problems. So, what exactly is a smart contract? At a high level, smart contracts are finite state machines that manage assets on a blockchain. For the purposes of this presentation, you can think of a blockchain as a distributed and immutable database. Here, immutable means that once data has been written to the database, it cannot be changed. So often, these smart contracts define financial applications, such as an open bid auction. In this finite state machine, the auction is initially running. Users alternate and submit bids until a manager stops the auction. Once the auction is stopped, users who lost the auction alternate and withdraw their bids. Smart contracts written in the Solidity language facilitate information flow between many users with unique addresses. An example of a Solidity smart contract interface is given here for the open bid auction. Here, each transition is now a function that can be called by a user. So, why do we care about verifying these smart contracts? To explain this, I'll walk through a simple scenario using the auction smart contract. Initially, a developer will sit down and encode the rules of a financial agreement, such as an open bid auction, as a Solidity smart contract. The smart contract is then deployed to the Ethereum blockchain as immutable code. Since the code's immutable, the developer won't be able to fix a bug in the code if one is discovered. Therefore, the developer better be sure that the smart contract is correct from the very beginning. The smart contract will then bring together users who do not trust each other, using the smart contract as a mechanism to ensure their cooperation. For these users to feel confident that they can trust the smart contract, they're going to want to know that the smart contract really is a refinement of the state machine we saw on the previous slide. This requires formal verification. However, manual verification is hard and often impractical, whereas automated verification is often limited. More importantly, smart contracts have two key verification challenges that must be overcome to solve this problem. But to understand these challenges, let's first take a closer look at the auction smart contract. So, the auction smart contract has three state variables. A variable manager that stores the address of the user who can stop the auction, the variable leading bid that stores the address of the largest bid sent so far, and the variable stopped that is true if and only if the auction is in its stop state. We represent these variables in this presentation by blue rectangles labeled by the variable names. Notice that each variable is set to 0. This is because all Solidity smart contracts are initially 0 initialized. A Solidity smart contract has 2 to the power of 160 users. Each of these users has a unique 256-bit address, and one address is even given to the contract itself. The address 0 is reserved as a null value. A smart contract can map user addresses to scalar values. In effect, this allows the smart contract to track user state. In the example of auction, there's a single mapping called bids that stores the bid of each user. We represent mappings in this presentation as sequences of orange rectangles. Notice once again that each rectangle has a value of 0. This is because smart contracts are 0 initialized. A special method called the constructor is called immediately after a smart contract is created. We represent methods in the following way. First, the name is given, then its arguments, then the user who sent the method called the message sender, and then the money paid to execute the method called the message value. In this example, the constructor is called, the manager is set to address 5, the sender has addressed 10, and no money is paid to create the smart contract. After the constructor has been called, the manager is set to 5 as expected. After the construction, the fee methods described before can be called by alternating users. A special note about bid is that the message sender cannot be the manager. This is to ensure that the manager cannot rig the auction in some way. Throughout this presentation, we represent ranges of possible values by corresponding intervals. So in this example, after some number of transactions, the auction is either running or stopped. Symbolic values are used to relate one variable to another. So after some number of transactions, the leading bid is non-negative, and the bid of this user is between 0 and the leading bid. So now let's return to the challenges of smart contract verification. The first challenge is that the state space is intractably large. In the case of auction, the bids mapping is going to store 2 to the power 160 values, each of size 256 bits. This is because there are 2 to the power 160 users, and each monetary value is 256 bits wide. Clearly, enumerating all states is not a verification solution that will work. Second, the maximum number of transactions in a sequence is either unbounded or intractably long. So for example, auction permits traces of up to 2 to the power of 161 plus 1 transaction. In such an execution, each user places a bid. The manager stops the auction, and then non-winning users all restore their bids. Clearly, smart contract verification is a hard problem. Current solutions range from random testing all the way up to manual proofs. All these techniques vary in terms of the properties they verify, their automation, and also the contracts they are applicable to. At a high level, they can fit into one of 4 categories. Declarative, static, and dynamic analysis techniques can be applied to all smart contracts, but can only find bugs. They can't verify the smart contracts. Model checking and symbolic execution, when applied for pre and post conditions, can be applied to most smart contracts with only a bit of work. However, the properties cannot span more than 1 transaction. Finally, next, we have model checking and symbolic execution applied to contract invariance. A contract invariant must be true across any sequence of transactions. These properties are deeper, and as a consequence, verification is harder, and often user guidance is even required to some extent. That's called semi-automated. Finally, we have deductive analysis and computer-aided proofs. These can verify any property, but they are often not very applicable because they require trained verification engineers and a lot of time to use. In this presentation, we focus in on verifying contract invariance through model checking. The main contribution of our work is a new way to look at smart contracts that enable highly automated verification while ameliorating state explosion induced by the number of users. So with that in mind, let's take a look at what our approach actually is. Our main insight is that it's often easier to verify a parameterized system for any number of users in a large instance of the system. To make this concrete, it would be easier to verify a small instance, a general instance of the auction smart contract with only a few representative users than it would be to directly verify the auction smart contract with all 2 to the power 160 users. With that in mind, the following verification procedure is derived. First, we generalize Solidity smart contracts to parameterized networks with control and user processes. There are now n users, and each user is conceptualized as a process where the mapping values are its state. The control process consists of our scalar variables and are sort of as shared variables between user processes. We then characterize communication patterns between user processes. So as an example, in the bid we looked at before, the manager and the sender communicate because the manager cannot have the address of the sender. We then identify groups of users that communicate and characterize interchangeable users. In the case of auction, we end up with 4 representative users: the null user, the auction itself, a manager, and the message sender. We then use these representative users to simplify analysis. This last step is best illustrated through an example. We're going to show that the bid of each user is at most the leading bid. To do this, we need an interference invariant, that is, an abstraction of each user process relative to the control process. Often these are simple, and in this case, that's exactly what happens. We find that the property itself is an adequate interference invariant. So our technique considers all possible executions and tries to find the reachable states. After each transaction, we ensure that the interference invariant is satisfied by each user process. In this example, that is the case because the bid of each user is either 0 or 20 and the leading bid is 20. We then use the interference invariant to abstract the state of each user. Now the users have bids between 0 and 20. We continue this process until we obtain an over-approximation of the reachable states of these abstract users. We find that the leading bid is non-zero and that the bid of each user is between 0 and the leading bid as desired. This verifies the property. In general, if we had violated the interference invariant at some point, a verification would be inconclusive. So how do we implement this in practice? The first step was to define an algorithm called PQG Builder that takes a smart contract and uses data flow analysis to automatically identify the groups of users that interact. We then introduced local bundle abstractions that take a smart contract and obtain the small abstraction with the representative users. So the preceding example was actually a local bundle abstraction that reduced from 2 to the power 160 down to 4 users. We then use software model checking, specifically Seahorn, to verify that the local bundle abstraction satisfies the provided property. If this system is safe, then the property is satisfied, and if we can find a violation, then the verification is inconclusive due to the abstractions, and a new interference invariant can be tried. To evaluate that technique, we compared to the state-of-the-art VerX tool and its benchmarks. First, we discovered that 8 of the 15 VerX benchmarks could be supported by SmartAce, and with sufficient abstraction, 12 of the 15 VerX benchmarks were supported. The 15th benchmark was only unsupported due to the complexity of abstractions that we were doing by hand. In principle, all of these abstractions could be automated, even for the 15th benchmark. We then found that all 12 conforming smart contracts could be verified by SmartAce. Even more importantly, SmartAce was able to outperform VerX in all cases. In 10 of the 12 cases, a speedup of at least 10 times was obtained when compared to VerX. Therefore, SmartAce performed very well on the set of benchmarks. So, in conclusion, smart contract can be sort of parameterized systems with many users and a single controller with shared variables. From this perspective, parameterized verification is necessary to ameliorate the state explosion induced by users. We've introduced local bundle abstractions that capture the behavior of any number of users by only a few. This abstraction is constructed automatically from the source code via static analysis and obtains a sequential program that can be verified using standard techniques. We've implemented this in a new tool called SmartAce, based on the Solidity compiler and the Seahorn model checker. This obtains order of magnitude improvements when compared to state-of-the-art techniques such as VerX. Additional evaluations can be found in the paper and our implementation and experiments are all available on GitHub.